GFCI breakers or branch circuits from GFCI receptacles will not protect low-voltage circuits of 24/12 volts that are transformed from 110 to 240 volts AC supplies in any low-voltage application, even if the 120 or 240 volts AC is GFCI protected. The reason is that GFCI devices are specifically designed to protect against ground faults in AC circuits. They function by detecting imbalances in current flow between the hot and neutral wires. If a GFCI senses a significant difference in current, it indicates a potential ground fault and trips the circuit. In low-voltage DC circuits, like those used in 24/12 volt applications, a neutral wire is typically absent. Therefore, GFCI devices are unable to detect ground faults in these types of circuits. To effectively protect low-voltage circuits from ground faults, alternative protection methods are required. This typically involves using a different type of protection device such as a fuse or a circuit breaker. The selected fuse or circuit breaker must be appropriately rated for the specific voltage and current characteristics of the low-voltage circuit it is intended to protect. Another option is to employ a ground fault detector. This device is designed to continuously monitor the low-voltage circuit for the presence of ground faults. Should a ground fault be detected, the ground fault detector will automatically trip the circuit, thereby interrupting the flow of current and preventing potential damage or hazards. Let's delve deeper into the operational principles of GFCIs and their limitations in DC circuits. A GFCI, or ground fault circuit interrupter, operates on the principle of detecting imbalances between the current flowing through the hot, or line, conductor and the neutral conductor. In a properly functioning AC circuit, the current returning through the neutral conductor should be virtually identical to the current flowing through the hot conductor. However, if a ground fault occurs, a portion of the current may divert from its intended path and flow to ground through an unintended path, such as a person touching a live wire. This creates an imbalance between the hot and neutral currents. The GFCI is designed to detect this imbalance, and if the difference exceeds a predetermined threshold, typically around 5 mA, the GFCI will trip the circuit very rapidly, usually within a fraction of a second. This rapid interruption of the circuit prevents sustained electrical shock and reduces the risk of serious injury or electrocution. In contrast, low-voltage DC circuits typically operate without a dedicated neutral conductor in the same manner as AC circuits. Instead, they usually have a positive and a negative conductor. Ground faults in DC circuits can occur when the positive or negative conductor comes into contact with a grounded surface or object. However, because there is no equivalent to the neutral conductor in an AC circuit, a GFCI cannot detect the current imbalance that would indicate a ground fault. Furthermore, the operational characteristics of DC circuits differ significantly from those of AC circuits, rendering GFCIs ineffective in detecting and responding to ground faults in DC systems. Therefore, alternative protection methods must be employed to ensure the safety and integrity of low-voltage DC circuits. Now, let's explore the alternative protection methods available for low-voltage DC circuits. Firstly, fuses are a common and effective means of protecting low-voltage circuits. A fuse is a sacrificial device containing a thin wire or element that is designed to melt and interrupt the circuit if the current exceeds a specified level. When selecting a fuse for a low-voltage DC circuit, it is crucial to choose a fuse with an appropriate current rating. The current rating should be slightly higher than the normal operating current of the circuit, but lower than the current that could cause damage to the circuit components or wiring. Fuses are relatively inexpensive and easy to install, making them a popular choice for protecting low-voltage circuits in a variety of applications. Secondly, circuit breakers are another widely used protection device for low-voltage circuits. A circuit breaker is an electromechanical device that automatically trips and interrupts the circuit when it detects an overcurrent or a short circuit. Circuit breakers are resettable, meaning that they can be manually reset after they have tripped, unlike fuses which must be replaced. Circuit breakers offer the advantage of providing both overcurrent and short circuit protection and are available in a range of current ratings to suit different circuit requirements. Like fuses, circuit breakers must be carefully selected to ensure that they are appropriately rated for the voltage and current of the circuit they are intended to protect. Thirdly, ground fault detectors are specifically designed to detect ground faults in low-voltage DC circuits. Unlike GFCIs, which rely on detecting current imbalances in AC circuits, ground fault detectors for DC circuits typically operate by monitoring the voltage between the DC circuit and ground. If the voltage exceeds a predetermined threshold, indicating a ground fault, the ground fault detector will trip the circuit, interrupting the flow of current. Ground fault detectors can provide a higher level of protection compared to fuses or circuit breakers alone, as they are specifically designed to detect ground faults, which may not always result in an overcurrent condition. In addition to these protection devices, proper wiring practices and grounding techniques are essential for ensuring the safety and reliability of low-voltage DC circuits. All wiring should be installed in accordance with applicable electrical codes and standards, and all equipment and enclosures should be properly grounded to provide a low impedance path for fault currents to flow to ground. This helps to minimize the risk of electrical shock and reduces the potential for damage to equipment in the event of a ground fault. Furthermore, regular inspection and maintenance of low-voltage DC circuits are crucial for identifying and addressing potential problems before they can lead to safety hazards or equipment failures. This includes checking for loose connections, damaged wiring, and other signs of deterioration. By implementing these protection measures and following proper wiring practices, it is possible to effectively protect low-voltage DC circuits from ground faults and ensure the safety of personnel and equipment. To summarize, GFCI devices are not suitable for protecting low-voltage DC circuits due to their operational principles and the absence of a neutral conductor in DC systems. Alternative protection methods such as fuses, circuit breakers, and ground fault detectors must be employed to provide adequate protection against ground faults in low-voltage DC circuits. Proper wiring practices, grounding techniques, and regular inspection and maintenance are also essential for ensuring the safety and reliability of these circuits. Remember to always consult with a qualified electrician or electrical engineer when designing or installing electrical systems, especially when dealing with low-voltage DC circuits. They can provide valuable guidance on selecting the appropriate protection devices and implementing proper wiring practices to ensure the safety and reliability of your electrical systems. It is also important to be aware of and comply with all applicable electrical codes and standards such as the National Electrical Code, which provides detailed requirements for the installation and protection of electrical systems. By following these guidelines, you can minimize the risk of electrical hazards and ensure the safe and reliable operation of your electrical systems. When selecting fuses or circuit breakers, consider the interrupting rating of the device. The interrupting rating is the maximum amount of fault current that the device can safely interrupt without failing. It is important to choose a device with an interrupting rating that is sufficient for the potential fault current at the installation location. Also, consider the ambient temperature when selecting fuses or circuit breakers. The current carrying capacity of these devices can be affected by temperature. If the ambient temperature is high, the device may need to be directed to prevent it from overheating and failing. Ground fault detectors can be particularly useful in applications where ground faults are more likely to occur, such as in wet or damp locations, or in industrial environments where equipment is subject to vibration or mechanical stress. These devices can provide an early warning of ground faults, allowing you to take corrective action before a serious hazard develops. When installing ground fault detectors, it is important to follow the manufacturer's instructions carefully and to ensure that the device is properly grounded. Proper grounding is essential for the effective operation of ground fault detectors. In addition to protecting against ground faults, it is also important to protect low-voltage DC circuits from overcurrents and short circuits. Fuses and circuit breakers can provide this protection. When selecting these devices, it is important to choose the appropriate current rating and to ensure that the device is compatible with the voltage and current characteristics of the circuit. Regular testing of fuses, circuit breakers, and ground fault detectors is essential to ensure that they are functioning properly. Fuses should be inspected regularly for signs of damage or deterioration and replaced if necessary. Circuit breakers should be tested periodically to verify that they trip properly under overcurrent conditions. Ground fault detectors should be tested regularly to ensure that they are detecting ground faults and tripping the circuit as intended. Proper documentation of electrical systems is essential for troubleshooting and maintenance. Keep accurate records of all wiring diagrams, circuit breaker schedules, and equipment specifications. This will make it easier to identify and resolve problems when they arise. When working on electrical systems, always follow safe work practices. Energize the circuit before working on it, and use appropriate personal protective equipment such as insulated gloves and safety glasses. If you are not qualified to work on electrical systems, hire a licensed electrician. Electrical work can be dangerous, and it is important to take the necessary precautions to protect yourself from injury. The principles discussed here apply to a wide range of low-voltage DC applications, including solar power systems, battery backup systems, and automotive electrical systems. In all of these applications, it is important to protect the low-voltage DC circuits from ground faults, overcurrents, and short circuits. Remember, safety should always be the top priority when working with electrical systems. By following the recommendations outlined in this discussion, you can significantly reduce the risk of electrical hazards and ensure the safe and reliable operation of your low-voltage DC circuits. Consider using shielded cables for low-voltage DC circuits to minimize electromagnetic interference. Shielded cables can help to prevent noise from other electrical devices from interfering with the operation of the low-voltage DC circuits. Also, use surge protection devices to protect low-voltage DC circuits from voltage spikes and surges. Voltage spikes and surges can damage sensitive electronic components. Select surge protection devices that are specifically designed for use with low-voltage DC circuits. Consider using redundant power supplies for critical low-voltage DC circuits. Redundant power supplies can provide backup power in the event of a power supply failure. This can help to ensure that critical equipment continues to operate even if one of the power supplies fails. When installing low-voltage DC circuits, be sure to use the correct wire size. The wire size should be large enough to carry the maximum current that the circuit is expected to draw. Using undersized wire can cause the wire to overheat and potentially start a fire. Follow all applicable electrical codes and standards when installing low-voltage DC circuits. These codes and standards are designed to ensure the safety of electrical installations. If you have any questions about the installation or maintenance of low-voltage DC circuits, consult with a qualified electrician or electrical engineer. They can provide valuable guidance and ensure that your electrical systems are safe and reliable. Remember that electrical safety is everyone's responsibility. By following safe work practices and taking the necessary precautions, you can help to prevent electrical accidents and injuries. These principles apply to both residential and commercial electrical systems. Whether you're working on a small home project or a large commercial installation, it is important to follow the recommendations outlined in this discussion to ensure the safety and reliability of your electrical systems.